Microsoft Fabric IQ Deep Dive, the new semantic, graph, planning, and AI layer for enterprise decision intelligence. Hello and welcome. In this deep dive, we explore Microsoft Fabric IQ, a preview workload designed to unify data across OneLake and organize it according to the language of the business. Fabric IQ helps organizations connect enterprise data, business meaning, relationships, planning workflows, and AI-driven experiences in one governed Fabric environment. Its central idea is simple but powerful. Data becomes more valuable when systems understand what the data represents, how business concepts relate, and what actions can follow. Fabric IQ brings together ontology, graph, plan, data agents, operations agents, and Power BI semantic models, so analytics, AI, planning, and applications can work from shared meaning and trusted context. The problem Fabric IQ addresses is familiar to many organizations. Data often lives across lakehouses, event houses, semantic models, reports, operational systems, spreadsheets, and external sources. Different teams may also define the same business concept in different ways. A customer, product, shipment, store, asset, sensor, or incident may have different meanings depending on the system using it. This creates inconsistent reporting, duplicated logic, slow onboarding, and unreliable AI responses. Fabric IQ helps reduce this fragmentation by organizing data around business concepts instead of isolated technical schemas. The goal is not just to unify data, but to unify meaning so dashboards, agents, planning processes, and operational workflows can use the same trusted business context. Fabric IQ brings together several Fabric items that work as a connected system. Ontology defines enterprise vocabulary through entity types, properties, relationships, constraints, data bindings, and rules through Fabric Activator. Graph provides native graph storage and compute for connected data, including nodes, edges, traversals, pathfinding, dependency analysis, and graph algorithms. Plan supports collaborative planning, reporting, analytics, data integration, management, forecasting, approvals, and write-back workflows. Data agents enable conversational question answering over governed sources, including ontologies. Operations agents monitor real-time data and recommend business actions. Power BI semantic models continue to provide trusted analytical models, measures, relationships, hierarchies, and KPIs, and they can also be used to generate ontology structures. The ontology item is the core semantic layer of Fabric IQ. It digitally represents enterprise vocabulary by defining the important business concepts in an organization and how those concepts connect. An ontology can describe entity types such as store, product, sale event, freezer, customer, shipment, sensor, route, or asset. It can also describe properties such as revenue, location, temperature, humidity, product category, identifier, or time-stamped operational signals. Most importantly, it gives these definitions a governed structure that can be reused across analytics, graph exploration, natural language agents, rules, and automation. This helps both people and AI systems interpret enterprise data through consistent business meaning rather than disconnected tables and columns. Entity types are reusable logical models of real-world business concepts. An entity type standardizes the name, description, identifiers, properties, and constraints for a concept so different teams do not redefine the same term in incompatible ways. Entity instances are the actual occurrences of those entity types, created from bound data, such as a specific store, product, sale event, freezer, or sensor. Properties are named facts about entities with declared data types, and they can represent either static attributes or time series values. Entity type keys uniquely identify instances and can be built from one or more string or integer properties. Together, these elements turn raw rows, events, and operational signals into standardized business objects that downstream tools and AI agents can understand consistently. Relationships are one of the most important parts of ontology because they make business context explicit. A relationship type defines how two entity types connect, such as store operates freezer, product sold in sale event, or customer places order. Relationship instances are the actual links between specific entity instances. These relationships can include direction, source, and target entities, cardinality, and source data mappings that connect keys from the underlying data. By making relationships first-class elements, Fabric IQ avoids hiding business logic inside custom joins, reports, or application code. This enables graph traversal, dependency analysis, connected reasoning, rule-driven automation through Activator, and more explainable answers to business questions involving interconnected processes and systems. Data binding is the process that connects ontology definitions to real data sources. It maps entity types, properties, and relationships to concrete data in Microsoft Fabric, including lakehouse tables, event house tables, KQL databases, and Power BI semantic models. Static bindings are used for descriptive information that changes infrequently, such as store ID, location, product name, equipment model, or region. Time series bindings are used for time-stamped observations such as temperature, humidity, pressure, energy usage, or operational telemetry. Fabric IQ requires static entity data to be bound before time series data can be contextualized correctly because telemetry signals need matching entity keys. This binding process transforms raw enterprise data into governed entity instances that can be previewed, queried, explored in graph scenarios, and used consistently by analytics experiences and AI agents. Fabric IQ can also generate an ontology from an existing Power BI semantic model. This capability is valuable for organizations that already maintain trusted analytical models with curated tables, measures, columns, and relationships. The generation process can automatically create an ontology item, entity types from semantic model tables, static properties from columns, relationship types from model relationships, and compatible data bindings where supported. However, generated ontologies still require governance review and domain validation. Users must validate entity keys, confirm relationship mappings, refine generated properties, and manually configure time series bindings because telemetry scenarios are not automatically inferred. This makes semantic model generation a strong accelerator for adoption while still requiring business ownership and governance to ensure the ontology accurately reflects enterprise meaning. The Fabric IQ documentation uses a Lakeshore retail tutorial to demonstrate these concepts in practice. The scenario represents a fictional ice cream retailer that combines sales analytics with freezer telemetry monitoring. Static business data is loaded into a lakehouse from datasets such as dim store, dim product, fact sales, and freezer. Telemetry data is streamed into an event house from freezer telemetry. A Power BI semantic model is then created from the sales and store data, and an ontology is generated from that model. The initial ontology includes entities such as store, product, and sale event. The ontology is later enriched with a freezer entity and telemetry bindings, so operational asset data can be connected with analytical business data in a shared semantic structure. The Lakeshore retail example is important because it demonstrates how Fabric IQ connects analytical and operational domains inside a unified business context. A traditional BI model might answer which products sold the most or which stores generated the highest revenue. A telemetry platform might separately monitor freezer temperature or humidity levels. Fabric IQ brings these worlds together by connecting stores, freezers, telemetry, products, and sales through ontology and graph relationships. This enables richer business reasoning across connected systems. Organizations can ask questions such as which stores operate freezers with abnormal humidity patterns, whether operational conditions correlate with product spoilage or declining sales, or how equipment performance impacts customer experience. This illustrates the deeper value of Fabric IQ, enabling enterprise intelligence that combines business meaning, operational signals, relationships, and AI reasoning without rebuilding logic separately for every analytics or automation scenario. The ontology preview experience allows users to inspect and validate instantiated business objects and relationships inside Fabric IQ. When data bindings are configured, Fabric IQ creates entity instances from source rows, records, and telemetry events. Users can open entity type overviews, review property values, explore entity instances, inspect relationship connections, and visualize time series signals associated with entities. The experience can display static property tiles, time series charts, and graph visualizations that help users understand how business objects connect. Time range filtering is also supported for operational analysis scenarios involving telemetry and event streams. This makes ontology more than a passive semantic definition. It becomes an interactive environment where users can validate whether the enterprise model accurately reflects real-world business entities operational behavior, and relationships. Graph in Microsoft Fabric provides the connected data engine behind many relationship-driven scenarios in Fabric IQ. Ontology defines what business concepts exist and how they relate, while Graph stores and computes over nodes, edges, traversals, and connected paths. Graph capabilities are especially useful for shortest path analysis, impact chains, dependency mapping, pattern discovery, and connected community analysis. In practical business scenarios, this could mean tracing how a transportation disruption affects downstream shipments, how a failing asset impacts operations, or how operational events propagate into customer or revenue impact. Fabric Graph supports interactive exploration experiences, including graph visualizations, query builder workflows, and GQL-style pattern matching. This gives Fabric IQ the ability to answer connected business questions that are difficult to express through traditional relational joins alone. The graph preview and query builder experiences make connected enterprise data easier to explore visually and interactively. Users can expand relationship graphs, add nodes, apply filters, configure visible entity types, run graph queries, and view results as diagrams, tables, or cards. In the Lakeshore retail example, users can filter a store entity by store ID to display freezers operated by a specific Paris store. They can also query stores connected to sale events where revenue exceeds a defined threshold. These scenarios demonstrate how graph exploration helps users analyze business paths and dependencies across connected concepts. Instead of viewing isolated rows or disconnected reports, users can understand how stores, freezers, telemetry, products, and sales interact as part of a larger operational and analytical ecosystem. Querying through Ontology is designed to let users ask business-level questions instead of requiring knowledge of underlying tables, schemas, or storage systems. Queries can begin with entity types, apply property filters, traverse relationships, aggregate across time, and combine analytical with operational context. The ontology layer can route requests to the appropriate Fabric engine, such as Graph for relationship traversal, Event House for telemetry and time series analysis, or semantic models for analytical calculations and KPIs. Fabric IQ also introduces natural language to ontology capabilities, where plain English questions can be translated into structured ontology-aware queries. This is important because business users often do not know whether data resides in a lakehouse, event house, graph model, or semantic model. Ontology provides the shared business vocabulary that helps the system interpret intent and retrieve meaningful answers consistently. Fabric data agents bring conversational AI experiences into Fabric IQ. A data agent can use an ontology as a governed source, allowing users to ask natural language questions grounded in entity types, properties, and relationships rather than physical schemas. In the Lakeshore retail tutorial, users create a retail ontology agent, connect the ontology as a source, and ask questions such as which stores have freezers with humidity below a specified threshold, or which products generate the highest revenue. The documentation also notes that adding the instruction support group by in GQL improves aggregation handling because of a known preview limitation. The broader significance is that data agents interact through business concepts instead of technical structures. This allows users to access connected enterprise intelligence through conversational experiences while still maintaining governance, semantic consistency, and trusted business context. Operations agents add another dimension to Fabric IQ by connecting real-time monitoring with business-aware recommendations and actions. While data agents focus on conversational analytics and question answering, operations agents are designed to monitor live operational signals, detect conditions, and support coordinated responses. In Fabric IQ, this aligns with the broader vision of intelligent agents that understand enterprise vocabulary through ontology and reason across connected operational data. For example, an operation scenario could combine live event house streams, ontology-defined entities, graph relationships, and downstream workflows to identify risks or recommend corrective actions. This is especially valuable for organizations moving from passive monitoring toward proactive and automated operational intelligence. Fabric IQ positions agents as consumers of governed semantics and trusted business context rather than isolated AI systems working from disconnected datasets. Rules and ontology powered through Fabric Activator integration allow Fabric IQ to support event-driven monitoring, alerts, and actions directly from semantic business entities. A rule can monitor a property across all instances of an entity type and trigger actions when defined conditions occur. For example, If freezer temperature rises above a safety threshold or humidity levels move outside an acceptable range, the system can generate alerts, notifications, or automated responses. This transforms ontology from a descriptive semantic layer into an operational intelligence layer capable of driving real-world action. Rules are created from the ontology experience and stored within Fabric Activator items, where they can be started, stopped, modified, and managed. This helps organizations automate operational responses while keeping the monitoring logic aligned with governed business concepts instead of embedding rules separately across disconnected systems. Plan is the collaborative decision workflow layer of Fabric IQ. It brings together planning, reporting, analytics, data integration, write-back, and collaboration into a governed no-code Fabric experience. Plan addresses a common enterprise challenge where budgeting, forecasting, and operational planning often happen in spreadsheets or isolated planning tools, while analytics and reporting exist elsewhere. This separation creates duplicated data, reconciliation issues, inconsistent targets, and disconnected decision processes. Plan helps organizations create planning workflows directly on top of governed Fabric data so business users can plan, analyze, and report from a consistent foundation. The experience includes planning sheets, PowerTable sheets, intelligence sheets, and InfoBridge capabilities that together help organizations move from insight to planning and from planning to coordinated execution within the Fabric ecosystem. Planning sheets support structured planning, budgeting, forecasting, scenario analysis, and collaborative business input. Users can create multidimensional planning models across dimensions such as time, department, account, product, geography, or business unit. They can generate forecasts using historical measures, formulas, driver-based calculations, manual adjustments, and rolling forecast logic as new actuals arrive. Planning sheets also support planning scenarios and versions so organizations can evaluate multiple assumptions without changing baseline operational data. Input rows and editable columns allow users to add manual entries, simulations, commentary, overrides, and business assumptions directly within the planning process. Write-back capabilities then persist planning outputs into supported Fabric destinations, helping organizations keep planning connected to governed enterprise data rather than isolated spreadsheets and disconnected files. PowerTable sheets focus on governed operational table applications, master data management, reference data maintenance, and business productivity workflows. They provide an Excel-like editing experience while maintaining synchronization with Fabric SQL databases and semantic model-backed data sources. Users can create table applications from existing databases, Excel files, CSV imports, semantic models, or direct business data entry. PowerTable sheets support forms, filtering, custom views, lookup relationships, calculated columns, row level and column level access controls, approvals, notifications, comments, audit history, and support for slowly changing dimensions. These capabilities are especially valuable for operational scenarios where business users require familiar editing experiences while organizations still need governance, traceability, synchronization, and centralized control across trusted enterprise data platforms. InfoBridge and intelligence sheets complete the plan ecosystem inside Fabric IQ. InfoBridge provides the data integration and preparation layer for planning, reporting, and analytical workflows. It helps organizations connect multiple enterprise data sources, prepare and transform datasets, manage refresh operations, and maintain consistent governed business data for downstream planning scenarios. Intelligence sheets provide no-code analytical experiences, including dashboards, KPI tracking, charts, tables, matrices, dynamic filtering, drill-through exploration, annotations, comments, scheduling, and content distribution. Together with planning sheets and PowerTable sheets, these capabilities support the complete enterprise decision lifecycle. Fabric IQ is therefore not only about semantic modeling and connected data, it also provides collaborative tools that help business users plan, analyze, govern, update, monitor, and act on enterprise intelligence within a unified Fabric experience. Tenant settings and environment prerequisites are essential for Fabric IQ because many capabilities are currently available in preview. Administrators must enable the ontology item setting before users can create ontology items. Graph preview settings must also be enabled so ontology-associated graph models can be created and queried. Data agent scenarios require enabling the data agent item type while Copilot and Azure OpenAI related tenant settings may be necessary for AI-powered conversational experiences. Plan capabilities require the tenant option that allows users to create planning preview items. In addition, workspaces must run on Microsoft Fabric-enabled capacity because Fabric IQ capabilities depend on Fabric infrastructure services. These requirements are not minor configuration details. Many ontology creation failures, graph loading problems, and agent experience issues occur when tenant settings, permissions, preview features, or capacity requirements are incomplete. Fabric IQ also includes important data modeling and platform limitations that organizations must understand before implementation. Ontology currently does not support versioning, and importing predefined industry ontology templates is not yet available. Ontology bindings require supported source configurations, and static entity data must come from OneLake-backed Fabric sources. Lakehouses that use OneLake security are currently unsupported as ontology binding sources, and ontology bindings support managed lakehouse tables rather than external shortcut tables residing outside the managed lakehouse environment. Delta table column mapping can also create compatibility issues for graph functionality. Each entity type supports a single static binding source, while multiple time series bindings can be associated from supported lakehouse or event house sources. These constraints are important because they directly influence enterprise architecture, data preparation, governance strategies, and ontology design decisions. Supported data types and entity key requirements are another important design consideration for Fabric IQ implementations. Ontology properties support types such as integer, boolean, datetime, double, and string, with mappings from supported lakehouse and event house source data types. Time series bindings support timestamp selection from datetime, date, and timestamp columns depending on the source platform. Entity type keys currently rely on string or integer-based property values to uniquely identify entity instances. The documentation also highlights that Fabric Graph has limitations with decimal data types in some ontology generation and graph query scenarios, which can result in null values appearing during graph operations. In these situations, organizations may need to convert decimal fields into supported types such as double during ETL or transformation processes. This means successful Fabric IQ adoption often requires careful data preparation and schema alignment before ontology modeling begins. Refresh behavior is another operational consideration that organizations must manage carefully in Fabric IQ environments. When ontology schemas change, downstream experiences can refresh to align with updated semantic definitions and relationships. However, when upstream source data changes, such as new rows arriving in lakehouse tables or event house streams, those updates may not automatically appear in ontology-driven graph experiences until a graph refresh operation is triggered. The documentation recommends batching updates instead of refreshing after every small data change because graph refresh operations perform full refreshes and can have significant capacity performance implications. Users can manage refresh operations through the Fabric Workspace scheduling experience. This means ontology and graph operations require not only semantic modeling discipline, but also operational planning around refresh schedules, workload management, and capacity optimization. Troubleshooting Fabric IQ often begins with configuration, permissions, supported source setup, and graph readiness. If an ontology cannot be created, required tenant settings are usually the first thing to verify. If an ontology generated from a semantic model has no entity types, the semantic model may not be published, tables may be hidden, or relationships may be missing. If generated entity types have no data bindings, the semantic model mode or backing lakehouse configuration may not be supported. If the preview experience shows no data, the issue may involve source permissions, table names, managed lakehouse table requirements, or access to the underlying Fabric graph item. If the graph looks sparse or incomplete, entity type keys and data bindings should be reviewed carefully. These troubleshooting patterns are important for real implementations because Fabric IQ depends on ontology, graph, source data, permissions, and tenant configuration working together. Capacity consumption should also be planned carefully. Ontology modeling usage is associated with ontology definitions such as entity types, relationship types, properties, and bindings when create, update, or delete operations occur. Logic and operations relate to activities such as visualizations, graph creation, graph traversal, Ontology exploration, querying, and refresh. Though the documentation notes that the ontology logic and operations meter is not currently in effect and users are billed through the underlying Fabric graph usage. Ontology AI operations are visible in preview, but not billed directly through that meter, with AI usage billed according to underlying copilot in Fabric usage. Graph cache storage is billed as OneLake cache. Administrators can monitor ontology-related usage through the Microsoft Fabric Capacity Metrics app. This makes cost governance, refresh planning, and capacity monitoring part of the Fabric IQ operating model. Lifecycle management is also relevant because Fabric IQ exists inside the broader Microsoft Fabric platform. Fabric supports Git integration, deployment pipelines, and variable libraries to help teams manage development, testing, and production workflows. Git integration helps multiple developers collaborate on workspace updates, while deployment pipelines help move content through release stages such as development, test, and production. Variable libraries help manage reusable values across workspace items and adjust environment-specific values across pipeline stages. Some CI/CD support remains preview-dependent, so teams should verify which Fabric IQ and related Fabric items are supported in their environment. As Fabric IQ matures, lifecycle management will become increasingly important for governing ontology definitions, plans, semantic models, graph artifacts, and related enterprise intelligence assets across workspaces. The strategic value of Fabric IQ is that it connects data, semantics, relationships, AI, planning, and operations in a unified Fabric experience. OneLake provides the governed data foundation. Ontology provides the shared enterprise vocabulary. Graph provides connected reasoning and relationship traversal. Power BI semantic models provide trusted KPIs, measures, relationships, and analytical structures. Data agents and operations agents provide AI-powered question answering, monitoring, and recommendations. Activator rules provide event-driven alerts and actions. Plan provides planning, forecasting, collaboration, reporting, and write-back. Together, these capabilities help organizations move beyond fragmented reporting toward decision intelligence. Instead of asking only what happened, teams can ask what is connected, why it matters, what actions should follow, who needs to respond, and how the decision should be captured. In conclusion, Microsoft Fabric IQ represents a major shift in how enterprise data platforms can support business understanding and action. It is not just a reporting layer, not just a graph database, not just an AI assistant, and not just a planning tool. It is a connected preview workload that uses ontology to define meaning, graph to reason across relationships, agents to make interaction and monitoring easier, rules to automate event-driven responses, and plan to operationalize decisions through planning, collaboration, and write-back. Because Fabric IQ is still in preview, organizations should approach it thoughtfully, validate limitations, enable the required tenant settings, prepare supported data sources, and design ontologies carefully. But the direction is clear. Fabric IQ is building a foundation for governed, AI-ready enterprise intelligence. Thank you for taking the time to explore this topic. Thank you for taking the time to explore this topic. See you in the next video.